So hello, everybody. Welcome back to the second part of our continuous shielding for safe reinforcement learning lecture. Today, I want to go to the second question that we asked last time. If you remember last time, we first talked about how can we check if an action that the reinforcement learning agent chooses is safe or not. And for that question, we looked into the tool called reachability analysis, which allows us to predict or to compute the set of states that the system is able to reach over time, given all admissible trajectories or along a given trajectory. And we can also use reachability analysis to predict how, for instance, unsafe states in the environment are moving over time. With that, we were able to look into the question, is my system able to reach unsafe states? If yes, then we know this action is unsafe. Or if it's not the case, especially for the over-approximative reachable sets, we know that the system is safe and we can safely execute this question. However, we stopped last time at the question, what happens if our action is unsafe? Let's say in this picture that you can see here from last time, our original trajectory is colliding with the unsafe states in blue, and we want to find an alternative plan in red that is safe instead. And this brings us to the second question, is how to synthesize motions or plans that are safe at all times. And we finished last time with the small example of control invariance, where we investigated the case that we have two policies that are safe in this case for the autonomous vehicle, given the finite time horizon, but only one trajectory in this case remains safe at all times, because at the end of our trajectory, we had the case that both trajectories end with a velocity that is much higher than zero, and the trajectory x1 will not allow us to replan our trajectory so that we can remain collision-free. Whereas the second trajectory, we can replan a new trajectory and then continue. This brings us to the concept of control invariance, or also called invariant sets. And it's a very important concept in control. And you can also see it related to some kind of stability. So what Hang presented in his lecture about the stability of control systems. And you can, figuratively speaking, consider an invariant set as a set of states for which you can always find a new safe plan. So if you're in the set, you are guaranteed to find at least one safe plan so that you can come to a next safe state for which you can again find a safe plan, some kind of recursive definition. So let's say we consider an arbitrary autonomous system. So we have no control input and we start with the initial state x0. Then a set xn that you see here is said to be invariant with respect to the dynamics of the system F if, when we start in this invariant set, we can remain in this set forever. Meaning, what you can see here, for all tau greater or equals our initial time, the state of our system will remain in this set. So basically, as soon as the trajectory of the system enters our set, we can remain in the set. So the system can just move around the set all the time, but it will remain in the set. And if the set is collision-free, for instance, defined, so there are always the walls for the drone in the beginning that we had, this set is free of all the walls, then the drone is safe because it can move around the set all the time, will never hit unsafe states. The cool thing is now with invariant sets is we can extend them to the case where we have not an autonomous system, but a control system. So we have a control input that keeps us in the set. In this case, we want to find control inputs so that we can steer the system in the set, or when we start in the set already, keep the system in the set indefinitely. So let's just consider a more general system in this case. So this system is a system where we have a control input U. We want to ensure that our state X remains in this certain set XD. Let's say that's collision-free. And we want to find a subset of those states that is invariant. So we know XD is the set of collision-free states, and we want to find a set that is either could be the same set or smaller, so that we can always remain and find a collision-free trajectory, safe trajectory, which can be defined as the set xn contains all initial states so that we can find a trajectory, an infinite long trajectory that keeps us in the set. Basically saying, if I'm in the set, it's invariant. If I can find a trajectory that's infinitely long so that my system remains in the set. And you can see this infinitely long trajectory as some kind of policy or control law. So if the system is then in this invariant set, it is guaranteed that we can find a trajectory to remain in this set indefinitely. So given again our set, we can find a policy or control law that keeps us in this set. This is very, very handy, especially for all our reinforcement learning problems where we have some safety or robustness. We want that our system starts in such a set so that our initial state is in the set, but also that the policy is always keeping us in the set. The question now is what happens if, let's say, this is the initial state here, and our policy would bring us outside the set. It's basically referring to our first question. It is becoming an unsafe action because it leads us away from our set for which we can guarantee safety. So as soon as we want to steer out of the set, we would like to find a policy or an action that, go back here, that keeps us in the system instead of steering us away from our set. And this is what we want to talk about today in the last minutes of our first lecture. I want to show you how we can kind of construct these invariant sets where we consider, let's say, a discrete system that you can see here. So we can obtain, given a control input u at a time step k, the next state xk plus 1. I want to talk about how can we see if this x invariant set, the set that you see here, is really an invariant set. And for that, I want to use the technique called backward reachability analysis. Last time we talked about forward reachability analysis only. And forward reachability analysis gives us the set of states that the system can reach over time, given an initial set. And backward reachability analysis is the other way around. We have given a target set, what kind of initial states can bring us into this target set. So if this is our goal set G, we go back in time, for which initial states x0 can we find a trajectory that steers us into our goal set. That's backward reachability analysis, and we will use that kind of technique here to define what is an invariant set. So the general observations that we can make is if our set, our candidate set for the invariant set is an invariant set, we know that if we are in the set, we can definitely find a control input u so that we are in the set again in the next step. So our current state, when we apply our control input, our next state xk plus 1 remains in that invariant set. That's a basic observation that we already have. Then we could see, what about we define a set x prime? So we start with our initial state so that the next state remains in our invariant set. If we would draw such a set, this could be such a set. Is that an invariant set? Unfortunately not, because you see, if I execute a trajectory that is here at the corner, there could be a state that is not in the invariant set. So it is not a candidate set. So, but if we look at this set, this is a candidate set of the invariant set because it's important that this x prime needs to be strongly either a superset or equal to the invariant set, meaning that every state that is here, for instance, we go into the target set again. And you can already see that when I look at that, this is basically the backward reachable set that contains all states for which we can find one control input that brings us into our invariant set. So showing us, let's say the x prime, in this case is our backward reachable set, the one step backward reachable set, R1b. We can see that our invariant set xis, we can reach that by computing what's the step, what are the states that are in the back, in the one time step backwards in time, those states that are able to reach that set. And we can see that in our illustration that R1b contains the set XIS, and all states that are in this set, we can reach our invariant set. The cool thing is we can, same as with the forward reachable set where I showed you this propagation method, we can do this kind of propagation method here as well. So I can apply the backward reachable set for one step again and obtain a larger set. I can do this over and over again until we have a break condition, that is our set is not changing anymore. So I do it the third time with another set, but the fourth time I execute this, I get the same set as the R3b. And you can see if we obtain a set that is not changing anymore, our algorithm converges. There are no more states that allows us to reach the step at the next set collision-free again. And you can call this the maximal invariant safe set, saying that these are all the possible states for which the system is safe for an infinite time horizon. These kind of sets and these techniques we want to use for reinforcement learning agents, can also use it in control in order to find if our system is operating in the safe domain of the state space. And for the invariant set, as I said, as soon as we obtain the set is not changing over time anymore, then we obtained our final maximal safe set. And that's the invariant set we want to obtain with. The interesting thing with that is we need to find a suitable terminal set to start with. So the initial rectangle that I showed you, this is an initial set that you need to choose. That is, for instance, minimal, and you know for sure I can stay safe. A lot of times you could, for instance, use a stationary set. Let's say you have an autonomous vehicle. A safe set for that one could be I am standing in standstill and I'm not moving at all, assuming nobody crashes into me. So it's you are not causing an accident on your own. In this regard, you can see this set of all states where the system is standing still as a safe set to start with. And then you can go backwards in time, saying like, okay, now I have velocity. Which velocity allows me in the next time step to stop in the safe set? And then you can go and build up a lot of dynamic trajectories that you can for sure know they are safe or not. Another way to look at these kind of systems is, for instance, for a helicopter. You can see a paper published in 2015. It uses also the invariant sets in order to plan safe maneuvers for a helicopter. And what they do here is they always try to find that after my trajectory or policy that I execute, I can append an emergency maneuver. In this case, these are the so-called loiter circles. And the loiter circle, especially for helicopters or UAVs, allows you to remain safe by just flying in circles all the time and remaining in this stationary trajectory. So what the authors do here is they compute a trajectory, the intended reference trajectory that you can see here in gray, and they verify that they are safe by appending this loiter circle, meaning if there are obstacles, if the loiter circle fits in there and the loiter circle is not hitting any obstacle, this one is a safe one. You can see that they have illustrate these two cases where we have one a valid and one an invalid case, because for the second, the right branch of our trajectory, the obstacles would be in the invariant set because the loiter circle is touching it. In this case, that's not a valid emergency maneuver, giving the helicopter the chance to collide with an obstacle, whereas the other one allows the helicopter to just fly in circles around. And this is the similar case that we want to obtain for a reinforcement learning agent. If we execute the current policy, can we obtain maybe a simple maneuver that keeps the system safe in case the next policy would not be safe, or the next policy execution? Here, the authors even consider disturbances. That's why they compute the reachable set of both the emergency maneuver as well as the trajectory. This is also what we looked into last time. And that's why we have these trajectory funnels instead, or trajectory tubes instead of just this regular trajectory. Another concept that is building very strongly on invariant sets are barrier certificates. And it's Barrier functions, you have heard it probably as well for that. That is very, very hot topic right now in control as well as in safety for systems, and more approaches in reinforcement learning are using that. So if you look, for instance, at the current last year's IROS proceedings or ICRO proceedings, you will see a lot of barrier function, barrier certificate papers, especially also applied to machine learning, because barrier functions, barrier certificates allow you to find a nice and neat way to prove if a given set is an invariant set or not. The interesting thing is barrier certificate is the name of a barrier function where you can prove guarantees for your system. And barrier function is just the original name that originates from the field of optimization theory. And the idea was back then that you could not encode proper constraints into an optimization problem, but instead said, I encode the constraint into the cost function. So the barrier was saying, as soon as I come close to my constraint, the costs are infinite. So if this is the cost function and your constraint is here C, and the costs are on the y-axis, you can see that I would give infinite costs as soon as I approach my constraint. Saying like, okay, as soon as I come close, for instance, to a wall with my drone, the drone gets infinite high costs. This kind of concept is now used and extended for the case of how can we prove that our set that we have right here is safe or not. So let's consider we have a safe set, in this case, just safe set C. And this safe set can be described by a function. So if you go back to our last lecture, you remember we had the set builder notation. So here we say that the set is represented as a function. In the set C are all states for which our function h of x is greater or equals 0. Meaning, if we are inside the set, it is greater than 0. If we are on the boundary, it's exactly 0. And if we are outside, it's smaller than 0. You can see that again. And then there is Nagumo's theorem from 1942 that says this set is invariant if I can show that for my system, the dynamics, so the derivative over time, is greater or equals 0, meaning that over time, our system, the h value can only increase for all states that are at the boundary of our set. This means that if I'm at the boundary of my set, and if my gradient is positive, so pointing upwards to more value, all these small vectors that you see here in the set, they're pointing in the set, meaning if you're in the set, you're trapped. Because the dynamics of your system, it's again an autonomous system, does not allow you to decrease the value, so leaving the set. Then we can, of course, extend it again to the case that we have a controlled system with a control input U. Then in this case, the extension of Nagumo's theorem is the set is invariant if we can find a control input so that our gradient of the dynamics is pointing into the set. So we always know there's a control input that makes the system go and stay in the set for all the states that are around our boundary. And this cool thing means that every time we approach the boundary with our system, we know there's at least one safe action that we can choose or safe control input so that we can go back into the set and stay there. So we are never leaving this barrier of the safe set. And that's why it's called also barrier certificate. So we are interested in defining a barrier property over the whole set, meaning we could say the naive idea is we want to find a function so that the gradient is greater or equals 0 for all the states at the boundary. Then we know that if we can go into the set, also the boundary, also the value on the gradient is within the safe set, also getting it higher. So what this means is every time if I'm in the set or at the boundary of my set, I can find an action that brings me into the set. And that's very strong. It's basically modeling something as a region of attraction. Every time I'm at the boundary, my system is drawn into the set and I stay there in the set. And with this gradient value, it means if I want to follow my gradient is always pointing, for instance, in the center of my set. our system might be stuck and always drawn to the center of the set, because it's very unsafe to go to the boundary, because you have less control inputs to use in order to stay in the set. That's why a lot of barriers functions and barrier certificates nowadays use the less conservative idea of scaling, meaning I use such a constraint which says my gradient needs to be minimally as large as the negative of gamma function, which is just a class K function saying it's linear increasing, for instance. But the important point is gamma of 0 is always 0. Then this scaling means if I'm in the safe set, my gradient does not need to be strictly greater or equals 0 anymore, but it can also be negative, let's say 8. Because if I'm in the safe set, I have more room. So I allow the system to move freely around the set inside. But as soon as I'm approaching my boundary, this constraint tightens up and does not allow these negative values anymore. So let's say I have this big set in the center. I'm allowed to have, for instance, greater or equals -8. So I can just move freely around in any direction with my trajectory. But as soon as I approach my boundary, it is very conservative again, and it says it needs to be stricter or equals 0. This means that our gradient must point into the set, because otherwise you don't allow gradients that point towards the set, towards the boundaries. So here the gradient is pointing to inside, and since we allow negative values here, our gradient can also point to the boundary again. So we can move freely around the set. The cool thing is now is people have shown that this is sufficient condition to show safety. And if we formulate it as, for instance, a quadratic program, a QP, then you will see this is, if you're familiar with quadratic programs, optimization in general, we want to find a control input u so that we are close to our desired control input, and we punish it as a quadratic cost function. The constraint to add safety is this one here, is just adding our control input must ensure this scaling barrier function. The cool thing is with that, you don't need to construct the whole set with backward reachable sets and so on, as I showed you before, but you just need to find a nice function h for which this scaling function works given your system dynamics. If this is true for your system, you can just add this to your quadratic program, and it can evaluate it on a point-based foundation instead of constructing the whole set before. When we go back to our original idea of the RL agent and the safety filter, we can now use the technique of invariant sets or barrier functions in order to design and check how can we find first, is the control input safe or not? And if it's unsafe, how can we modify it so that it becomes safe? In the previous slide, you saw that it will find something that is close to our desired control input so that the constraint is fulfilled. Meaning, if we have that for a safety filter, you allow the reinforcement learning agent to execute the control input on the system if it's safe. Otherwise, you want to find the closest action or control input so that it is still safe and keeps you in the safe set. So the RL agent in this case is planning a desired control input. If U desired is safe, we execute the actual control input is our U desired. However, if this U desired is unsafe, we modify it so that U actual of X minus U desired of X, they are very close, subject to barrier function. And that's the trick here. So we can use our standard reinforcement learning system. I've never made any assumption on the reinforcement learning system. As soon as we get our policy, we can impose this model-based constraint on top that just says if the policy executes a desired control input that is safe, we don't modify it. In case it's unsafe, we modify it, but we quantify it as least as possible. And this is also often what you want in safe reinforcement learning or robust reinforcement learning, to have minimally intervening safety layers, saying like my safety layer only intervenes when necessary. And if it intervenes, it should try to keep our desired policy output as our actual input as close to the policy that we optimized. I want to show you a nice example in the next slide. But here, before we go there are some things that you need to consider for barrier certificates. In this case, usually it's point-wise optimal. So what you do is you just look at the point, at the state that you're currently looking into. So we have a one step that's really nice. You don't need to iterate and compute the whole set like we've done in the invariant set with backward reachability analysis. And for certain systems, you even have closed form controllers, so you don't need to optimize at all. It's really cool. You can always use the controller instead. When we go back to Hang's lecture, where you showed control Lyapunov functions, then the cool thing is it has been shown that control Lyapunov function is a special case of a control barrier function. And also, when you go back to your robotics or introduction to robotics classes, the artificial potential field approach is also a special case of a control barrier function. And if you remember, artificial potential fields model obstacles as a very high potential so that you don't bump into this mountain that is representing an obstacle. And this is basically a similar kind of concept for a control barrier function. You try to be in the valley, that's the artificial potential field, and never increase the energy, the potential, so that you can bump to an obstacle. The theory can be extended to discrete systems as well. So if you have a discrete system, you can still use control barrier functions. There are extensions on that. And there's a really, really cool paper by Aaron Ames from 2019. It gives you a really nice introduction tutorial kind of style for control barrier functions, what they are about, how you can derive them, and a lot of examples. One of the examples is one example where they define the control barrier functions for a Segway. The idea here is the safety is to keep the Segway upright. What they define is a control barrier function that defines a safe set. You can see here on the left side the projection of it with between the red lines, and in green the system trajectory. The top video, there is no safe set. It's just a controller that executes this, whereas the second one, it modifies the control input if the system is about to leave the safe set. And then you can see how different this is for our application. So you can see the video. This is without the safety controller. It does not, and with this safety controller, it reacts to I'm close to leaving my safe set. You can see that. And the controller kicks in and stops the Segway, whereas on the first case, it's not aware of, oh, in this case, I will tip over and will not be able to recover, whereas for the second, you explicitly encode that for certain pitches, you can keep the system safe. In this case, what is it? Minus 15 to 15 degrees. And by having a controller that detects I'm leaving this pitch, I will go back to my original state and keep the system safe in this regard. So let me show that important part again, where you can see that as soon as we are detecting that we are leaving the set, the other one is leaving the set, the first one, and the second one that uses the control barrier function is trying to stabilize the system by keeping it in our safe set. And you can imagine that instead of a PD controller that is there, you can have some neural network, some reinforcement learning policy that provides you this control input. And with the safe set constraint on top, we can modify it only if we are about to leave the set. But as soon as we are in the set, the policy can move and explore whatever it wants to do. The last thing I want to talk about today before we close this chapter of continuous shielding for safety explicitly is Gaussian processes, because that's also very recently that people use Gaussian processes to estimate a stochastic version of an invariant set. If you have not worked with Gaussian processes so far, Gaussian process represents distribution over function. So any state x is assigned a random variable r of x so that you can model a distribution of function as a prior using a given data set. Here's the theory where you define the random variables, you have the mean and the kernels, and the kernels defining how samples that you have of your function correlate. And in the beginning, the Gaussian process, if you model it, is model a certain function, it can be any function. The more information you get, so the more samples you have, you narrow down the distribution and get more information. I will show you how this looks like on an illustrative example in a moment. But the important part is the kernel that says how two samples are correlated. For instance, you can use an exponential kernel that you can see here. But what the Gaussian process is doing is, given a data set of samples, it can compute the posterior of what is the distribution looking like. So if we have an initial Gaussian process, you can see the mean as, for instance, 0. We take the red color, and we have some mu 0, and we have some standard deviation of our Gaussian process. That's why there's this rectangle. And we can generate samples of these functions. Let's say the yellow function, the green function, the red function. All these dashed lines fit to our current mu and variance of our Gaussian process. When we now get another sample, or in this case, even multiple samples, we know in this case, the function needs to go through the samples because we got samples of our system. We could see it as, for instance, the dynamics of the system. Then the mu, our mean of our Gaussian process for each of these samples is 0. And with that, we narrow down the search space, or the distribution that can model certain functions in our Gaussian process. So you see, in this case, the functions that I can generate, the samples, are much, much more similar because they need to go through our 5 samples. I can do this also with samples that are uncertain. So let's say I have some noise. Then instead of having a mean of 0 at each of these samples, I have a mean that is greater than 0. And with that, I can also model some noise. But the cool thing is, with Gaussian processes is, I don't know how my function looks like, but I get some samples that give me more information of what my function could look like. And we can use it to model variance sets, or in this case, safe sets. So the idea is we get a set of samples and a value of our safe set function. So if you remember a barrier function, you could say everything that has a value of greater or equal 0 is in the set. Everything that is below 0 is out of the set. If I say it's binary thing, -1 is out of the set, 1 is in the set, I can get samples that someone labels, or you can do automatic sampling. And here on the right side, you can see how this Gaussian process models the safe set. So every time I get a red sample, I say this was in the safe set, whereas every time I'm out of the safe set, it's a blue sample, it is getting a negative value. And over time, with all these samples, you can see that this models an ellipsoid in our state space that is our safe set. So basically, we optimize a probabilistic version of our safe set without guarantees by getting estimates from unseen parts of the state space. And then we build our safe set online. So you could say I start with my system being very conservative, I explore a bit around my state, get more information, is this safe or not? And if it's safe, you add it to your Gaussian process and get more information about it. There's a really cool paper that used this kind of technique to approximate the set of safe control parameters for a drone, which I want to show you right now. If you want more information about Gaussian processes, I really recommend the book of Rees and Roberts. Gives you everything you need to know for Gaussian processes. But let's look at an example. What the authors did here is I have a controller that has certain parameters. In this case, the controller gain K1 and the controller gain K2. And I want to find the set of safe parameters K1, K2, so that my drone is stable and safe. What they do is they test certain K1, K2 pairs and get a performance value and use this performance value to approximate this safe control gain function that you see here as a heat map kind of. And the cool thing is every time you get a sample, you approximate your set and you can compute the gradient. so you can steer what kind of sample you want to query next. It is really, really nice if you see it in a video. So that's why let's have a look at the video where you can see how the Gaussian process is used online over time by getting more samples. So in the beginning, you will see on the right side that the sample, that the safe set says everything has the same value. But if I get one value, this is the performance value. I know, okay, here's a bump, this is the performance I have. So I get another value. And you see how the set is improving over time, given the performance. So I know where to sample next, where I get more performance. You do this over time with more samples, and you build the set of very well performing controller gains. Instead of building the safe set or this controller set with model knowledge, you just need some samples, much less samples, by getting the performance and building it over time. You see, it's now experiment 28. And at experiment 30, but just with 30 samples, they found the optimal controller parameters so that they have an optimized controller. And this is the power of Gaussian processes that you can use for your system as well. So instead of you having the exact model knowledge, because for certain systems, we don't have the dynamical equation. In this case, you can use samples and the labeling function in order to provide you an approximate version of your controller parameters or even safe set. This brings me to the end of our first part on continuous shielding. I hope you were able to see that we can use shields as well for continuous domains, and that reachability analysis is a really neat tool to detect future unsafe situations. Persistent feasibility, or how we used it later as control invariance, is important to keep the system safe. So we need to look at infinite time horizons so that we never run into an unsafe state. Invariance sets allow us to constrain our systems to remain safe, and also to restrict actions that are unsafe, that are leaving the set, so we can not execute these actions, but instead execute actions that keep us in the set. I showed you that control barrier functions are also a nice way to model these kind of safe constraints. And Gaussian processes can be used to approximate safe sets given samples of the system, and for instance, a performance metric or a function that is giving you similar values as a control barrier function. And lastly, what we want to achieve is we want to synthesize least restrictive shields, meaning our shields are only intervening when the system is getting unsafe, similar to the Segway example. And we have a model-based world where, for instance, if we have the model of the system, we can construct these invariant sets analytically, or the model-free world where we have some Gaussian processes that can use samples in order to give us a kind of model for our safe set. And there are also more things that you can integrate, such as uncertainty, as well as partial observability. This brings me to the end of the talk for today. I hope you learned a lot of new cool things that you can apply for your own system for reinforcement learning and for safety and control. Next week, I will talk about how we can use shielding to correct policies even more by combining shielding with human feedback to obtain policies that are perceived as safe by the users of a system. So we adjust the shields online, or how we can use shields to correct a policy that fails because certain things in the sim to reality gap are not modeled. How can we use shields to correct policies even though we have deployed them already on a real robot? Thanks for listening today. I look forward to see you next time, and have a great day. Bye-bye, everyone.